And real quick, now that we're recording, if it's all right, just a quick intro before you get started, Danny. I would like to just give a little overview of everything that we have set up for the hackathon so that folks who watch this video will also get a little bit of an overview of what we're trying to do here, the process for how you engage with the hackathon, and then we can turn it over to you in like 2 or 3 minutes. Does that work for you? Okay. So, folks, very excited. Tomorrow, Friday, February 2nd, will be the official launch of the hackathon. I have a little basic set of instructions for how to participate. The basic idea is you are part of this GitHub repository for the hackathon. And all of these challenges here, there's some challenges from Inflection, some challenges that I've created, some challenges from NVIDIA. And the goal here is really to give you the opportunity to try any of these. So the workflow is you will fork this repository. So you'll make a local copy of it on your own side of GitHub and be able to modify the hackathon challenge guides where you will be submitting your code. So as I mentioned just now, let's say you are going to tackle this one of these NVIDIA hackathon challenges that our friend Mark here in the call will be speaking to in a moment. So the way that would work is you download this Jupyter notebook, which contains a lot of the useful information for the hackathon. For example, this first challenge requires you to implement adapt VQE. So there's a reference here that shows you what that is, what adapt VQE is. And notice that each hackathon challenge now has associated with it a prize pot. We've got 3 levels of challenge: easy, medium, and hard. Those have different prize pots associated with them. And the first person to create code that solves the problem, and then the way you submit your code from your forked repository is you submit a pull request. And then that pull request will kind of log the time that your solution was submitted. And if multiple people submit solutions to a problem and they're all correct, the person who submits first will get that prize for themselves. Now, this is obviously a team sport. This hackathon Quantum Research Exchange team was all working together, and the team's success will be measured as a proportion of how much of the total prize pot, which I think is about $2,000, how much of that total prize pot your teammates have won. So hopefully that encourages teammates to work together, collaborate, and so forth. I did want to draw your attention to one more thing. I just pointed out this adapt VQE challenge from NVIDIA. I have actually created a warm-up challenge, which has its own prize money associated with it, that is designed to help you get started thinking about that NVIDIA challenge, where I give you the chance to learn about what regular garden variety VQE is. And then this is example code from Xanadu's quantum package Penny Lane that shows you how it works. And the goal is, with all of my warm-up challenges, the goal is to convert that code into CUDA Quantum to run it in the format that NVIDIA has provided. So that's a good overview of the challenges, the prize money that's associated with them, and how you submit solutions. Now, what we're going to do, if you actually are going to compete on this NVIDIA challenge, you're going to need access to high-performance computing power. You're going to need a supercomputer, and that is Danny's domain. So I'm going to stop my screen share and introduce Danny to everyone. Hi, Danny. Danny's here to help all of us, myself included, get ourselves set up so that you will have the ability to run your code on a personally allocated NVIDIA chip. So with that, I'll let Danny get us started.
Yeah, hi everyone. So just a little brief background. I'm part of the Jetstream 2 team. We're sort of based in Indiana at Indiana University, but our supercomputer is available to anyone in the country. We are NSF funded, so it's nationally funded. So yeah, we're here to sort of provide some of the infrastructure, specifically the NVIDIA GPUs that you'll need to do those parts of the challenges. So my job here today is to show you how to get access to these instances. And we're going to sort of walk through that. And hopefully you'll learn a couple others sort of useful tools along the way, like how to SSH into an instance. So yeah, I guess to get started, I'm going to share my screen. And give me a sec. So I assume you will have access to that GitHub repository. Go ahead and pull that open. And once you get here, you'll find almost all the way down, there's NVIDIA Jetstream 2 Setup Guide. And go ahead and click on that. And just give me like a thumbs up once you pull this up. Was that everyone's thumbs up? Sorry if I missed you. Okay. Abby, were you able to get that pulled up?
Yeah, I just got it pulled up.
Okay, awesome. Um, so the first step is to get into your instance, and this will just be what's called SSHing into your instance. Basically, it's a secure way to remotely connect to your instance. Now, in order to run this, you're going to need to open up a terminal on your computer. So if you haven't done so before, I'm unfamiliar with sort of your knowledge going into this, but go ahead and open that terminal in Windows. You can, if you type in terminal, I believe it'll pull up and you can open that. It'll be probably similar. It might be called like command window or something in Apple. But yeah, go ahead and open up that terminal. I already have a terminal open. I'll show you what it might look like once you're in here. Mine's going to look a little bit different because I've customized it a little bit. But once you pull it up, you should be able to start typing stuff into that terminal. I guess we'll just keep going with the thumbs up once we are sort of caught up, or nods, or yeah. Okay, awesome. I see some nods and thumbs up. You will need, in order to connect to the instance, you'll need a IP address and a password. Did you, to get that, did we send those out, or do we need to?
Danny, I saw you message saying that you were going to send it, but I don't think I saw the
Oh,
email that actually contained those passwords.
okay, let me double check. Oops, hold up. Let me just double check on that.
And since it's a smaller group today, it might be, kind of easy. One thing we could do, I think, is just direct message to
Yeah,
the three of
yeah.
us, just password instance.
Hmm.
And then we can follow up with emails so that people have it saved in their records what their password is.
Hmm. Let me go ahead and do that now. And I'm going to send you the link to that. And then, do you mind DMing Abby and Jacqueline, just 1 and 2, or however you decide to do it?
Yes. So is the password these like collection of 3 and 4 letter terms? Like
Yeah,
like a
yeah,
string of them?
yeah.
Okay.
It's randomly
Interesting.
generated long string.
Okay. Abby, coming to you first. I just sent you your IP address, and coming next, the password. Can you confirm you received those? And Jackie, I'm moving to you after that. Okay, so Jackie, you should be getting yours. IP and password. Did you get those two? Great.
Yes, I got that.
And then I'll just use the number 3 for myself.
Okay. So let me share my screen again. Great. So the way you'll access that instance, the first thing you'll need is the IP address, and you can copy these instructions from the GitHub. So that first one is going to be SSH, and then the default user that we have on our instances is called XO user. So you have the username, and then you have to put in the IP address. And I already had that here. So for my instance, I have this given IP address, and you're going to put yours in there. And it might ask you something about like, are you sure that you can verify the authenticity of this? And you'll just type, yes, I'm sure. And then it'll ask for the password, and now you can just input the password here. Depending on your terminal, if you copy paste, you might have to like right click and then choose paste. Also, it won't typically show the actual letters, and that's just like a security thing. So I just pasted mine, but you can't actually see that I put anything in, so you might see the same thing there. But I'm going to go ahead and hit enter. It should connect me. And I'll give it a minute, make sure that we can actually get into these instances. So let me know when you have gotten in, or if you have any questions. All right, Jacqueline, thank you.
It's saying that there's no host found from
No host found.
that.
Double check that you had the XO user in front of the IP with the @ sign. Does that look right? Okay. No host found. Does it say anything else, or just we can also, since it's pretty casual, we could try sharing screens as well. Might help for diagnosing some of this stuff.
Yeah, I can share my screen if you'd like.
Okay.
So it's just showing.
Oh yeah, so get rid of the brackets around. That's my bad. I should have explained that.
Oh,
Yeah. Anytime there's brackets, we just that means replace everything, including the brackets. Yeah, my bad for not explaining that. And still, was there an extra colon at the end?
oh yeah. Wait, no.
I see a colon at the end.
Yeah, Abby, just press the up arrow on your keyboard. And then delete the colon from the end of your line. Try it again.
There we
There
go.
we go. Now type yes.
Yeah. Yeah, type yes and hit enter. There we go. And now you can enter that password, which you should just be able to copy and paste in. Okay. Great. All right, so now that you've gotten in, you're going to have to pull down the NVIDIA CUDA Quantum packages, and this might take a minute, but let's go ahead and get started on this. So this next line here on the guide, just go ahead and copy this and paste it right into your terminal now. And this will take just like 2 minutes or so. It's pretty fast. Give that a second. In the meantime, I'll make sure that we're all hooked up and this is running at least. So what we just did here is something called Docker. It's sort of a tool that sort of packages not just one piece of software, but a whole bunch of pieces of software together so that you can sort of, it makes it really easy to get your sort of setup on your system just the way it needs to be, with all of the different software and bits and pieces that need to be installed. Okay, it looks like mine just completed. Go ahead and give me the thumbs up once you guys have completed. Is it running for you, Abby?
It's saying that connection is closed, which is weird.
Connection closed. Oh, wonder if, go ahead and if you go up on the up arrow, you should be able to connect back to your instance. You'll know that you're connected if you see down here at the bottom, or here, let me just clear my screen so it's up at the top. Oh, come on, there we go. You'll see this, it should say EXO user at CQ Hackathon, and then 1 of 19 or 2 of 19 something. If you don't see that, go ahead and SSH back into the instance using that previous command. You might have closed the connection if you tried to paste or something. Try using right click and then selecting paste. Let me know if you're still having trouble getting back into your instance. We can figure something out.
I'm gonna start sharing my screen because I'm like kind of confused.
Yeah, that's fine. Yeah,
Literally what this time is here for. We're
yeah.
once we've gotten everyone into the VS Code on your instance, then we'll be able to run or follow along with the tutorial that Mark is going to walk us through for CUDA. So we're doing fine on time.
Yeah, so I re-put the code that you gave me, the username, saying can't resolve. Oh, did the same thing I did before.
And feel free to share your screen if you want us to. Provide a little more help.
Abby, are you still stuck or do you want to share your screen?
Now can you see my screen? Wait, no. Can
Oh,
you see
there
it
it
now?
goes.
Yeah.
Now I can.
Oh, make sure to not capitalize the EXO user. I think that might make a difference.
So this little user thing.
Yeah, so go ahead, if you press Control C, it'll cancel, or just hit enter and it'll deny you. And get to a fresh line. Or hit Control C.
Yeah.
Okay, so then, yeah, type in the SSH, and then exouser at, and then your IP address. And then, yeah, no colon at the end though.
Oh yeah.
And one trick to save some time, if you press up on the keyboard, it will just copy the previous. Yeah. Okay, yeah, now go ahead and copy and paste that password in. Are you right clicking to paste it?
Wait,
Okay,
right.
make sure to only hit right click once, or else you might be like pasting it twice.
Okay.
Joan, can you maybe make sure that the password got copied correctly for Abby?
Yeah. Abby, you were able to get access previously, right?
No.
You might
No,
want
you-
to start it as well, Danny. You might want to see if she hit the fail to ban.
Oh. Too many attempts, you think?
Perhaps.
I'm just trying to pull up the set of passwords. I copied it from the spreadsheet, so Abby should have received the correct one. But just to
Yeah, let
make
me
sure.
just verify that it works on my end. Okay, let me make sure. I was able to get in on my end. Let me make sure it hasn't. I'm gonna go ahead and start that download for you so that we can save a little time there. I'm just doing the next step for you, but let me make sure that. I don't think there's anything that should be blocking you.
Does it make a difference that the SSH was capitalized?
Oh, I don't think so, but it's worth a try. Yeah.
Okay, and then Abby, I resent you your password. So just select Control C and then click on the cursor and Control V.
Do we want to try? Well, we could try number 4, Joan.
Sure. Yeah, that's fine.
Yeah.
Just want to keep make sure we're keeping an eye on the time. How much more time do you think we'll need, Danny, if we can get past this
Yeah.
step?
We can, yeah, if need be, I mean, we can just try to figure this out at a later time, and just continue on.
Let's just try one more time. So Abby, I'm just gonna send you a new IP address and password. And if that doesn't work, we can I have Danny and I have everybody's contact info, so I can put you in touch and you guys can troubleshoot. We'll get you on here.
Yeah.
And to get out of the password one.
Oh, Control C.
Oh, yeah. Cool.
Yeah, that'll just cancel the last thing. Mm-hmm.
Just keys.
Good. So say yes.
And then just paste it once and hit enter.
Hey.
Awesome. That worked. Yeah, I don't know, maybe there's too many failed attempts and it automatically blocked. That's okay, we'll use this one. Okay, let's go ahead and do that previous step now that I know you're caught up, which is from the guide, copy. Let me share my screen again. From that guide, Abby, go ahead and copy this line here, the Docker pull line. Copy that whole line and then paste it into the command line and hit enter.
Hey Danny, I've run into an issue. Maybe you can talk me through.
Sure.
So
Well, yeah, 'cause that'll take.
on my side, I followed the instructions through the VS Code setup, and then put in a unique name, followed the link to the GitHub, entered the code, it said it was successfully connected. But I'm not getting a link to open VS Code.
Okay. Well, we can, once we get to that, I'll be able to tell you, you can just use that name that that you entered, and there's like a URL and there's a spot in the name to like just fill that in.
Okay.
So yeah. Okay. Abby, I know that might still be running, but go ahead and just let that finish. And once it finishes, you see the command line pop back up. But for the rest of us, let's go ahead and copy this next one. And Abby, once it finishes, just copy this and enter it into your terminal.
Jackie,
copy
where are
that.
you at? Where are you at in this setup? Did you get ahead while we were working on Abby's issue, or are you waiting at a particular step?
No, yeah, I was just waiting for the next step, and now I'm gonna do the most recent one.
Okay.
Okay, awesome.
I'll just flag for time. I had asked Mark to be able to do his presentation in about 15 minutes, but I do want to
Okay.
end at 11:40 just so that he has extra time there.
Yeah.
Thank you for your
That
patience,
sounds
Mark.
good. And
Oh yeah, no worries at all.
and yeah, if we don't get through everything today, we can, finish it another time. Okay, so yeah, go ahead and enter that next line in. And this essentially just runs this Docker container. And this is sort of has all the software you need to run CUDA Quantum and everything. It also has a built-in VS Code server stuff set up. So all we have to do is run a line to actually start a server. And this will let you actually modify code and everything on the server directly. So I'm going to copy this next line here, but don't enter it quite yet. You're going to make a couple changes. So I'm going to enter it here, and then I'm going to scroll over with the arrow. And where it says unique name here, go ahead and delete all of that. And we're going to just enter some sort of unique name. So for me, I'm just going to do it's CUDA Quantum dash, and then I'm going to use my initials, and then I'm just going to do some numbers or something here. It doesn't really matter. You can just put one number or something.
I just put my name.
Yeah, or just put your name, just something simple that's unique. And then hit enter. And it should ask you, how would you like to log into Visual Studio? And you can scroll down to where it says GitHub account and hit enter there. And once you do that, it'll say to grant access to the server, please log in and use this code. So I'm going to go ahead and open this, copy this here, and paste that into a browser. And I have already logged into my GitHub on this browser, but you might have to log into your GitHub account here. And then copy that code, that 8-digit code, and enter it into here. Well, I was hoping copy paste would work here. There it goes. And then it'll ask, do you trust this? And we're going to say, yep, authorize Visual Studio Code. And then a little check mark will show up saying, congrats, you're all set. If you go back to your terminal, okay. Let me know when you get.
This is what happened to me. Like everything worked, I just didn't get the URL.
Yeah, that's so interesting. Every time I did this before, it showed a URL.
But you said the URL is generated in some sort of predictable format, yeah?
Yeah, it is.
It might behoove us to just put that into the setup guide in case it doesn't populate in the terminal.
Yeah, I agree. Let me. I'm gonna try rerunning the previous line.
No, I don't.
I'm gonna see if I can get that to populate this time.
What is the URL format, Danny?
Don't remember. I'm hoping that I can get it to work this time.
Okay.
Yeah, I don't know. It worked for me the second time.
She does not get partial credit.
Okay. The only thing I did different, so I just tried it a second time, and I didn't think this would make a difference, but the only thing I did different is I control clicked this link rather than copy pasting it to my browser. I don't know why that would make a difference, but it's worth a try. Jacqueline and Abby, have you had luck with this? How did this go for you?
I was able to do it and I got the Visual Studio link.
Oh, you did? Okay, awesome.
Mine's saying no link found,
No what found?
no file found.
No file found. Does yours look like, do you have this sort of prompt here that has something like CUDA at a bunch of stuff, letters and numbers? Okay, you may have missed this step here, did you copy and paste this line
Yes.
into your terminal? You did? Go ahead and try that again. And it should put you in, you should see this sort of NVIDIA CUDA Quantum message show up, and you should see something like CUDA Q at a bunch of letters and numbers. Joan, were you able to get the
I have
VS Code link?
open. Yep.
Okay, awesome.
It still says no
Yeah, we might have to, I think we're on time, so we might have to figure that out offline sometime.
Yeah.
I swear to God, I looked at it, I'm like, okay.
So yeah, if you did get the populated link, go ahead and open it. And that'll bring you to your Visual Studio Code where it should connect, and it'll ask you, do you want to use your Microsoft or GitHub? We chose GitHub, so I'm going to choose GitHub. And it's going to open up the remote host. And it might take a minute. Mine's sort of stuck on opening remote down here. I've had this problem in the past, and if I restarted the, oh, here we go, it just finished. I think connecting, I got a connecting message. There we go. It just took a minute. So now I'm in my Visual Studio Code. From here, I can click clone repository. And if I copy this URL here, so actually let me go back to the main Quantum Hackathon URL. If I go ahead and copy this and I hit clone repository, and then I'm going to clone from GitHub and then put the repository name and then enter, go ahead and enter. Yep, open it. And it'll take a minute. Yes, I trust the authors. And there we go. We have that repository cloned. So now you can access these Python notebooks here.
Thing that looks like an older version of the repo. Anyway, we should probably move on to Mark's.
We can move this on, yes. Thanks for your patience.
Yeah. Thank you so much, Danny. I think we'll be following up with some questions. I got into Visual Studio Code, but it told me tunnel Joan not found, where I named my server Joan. So we'll get this up and running, but for now I think it's time to turn over to Mark. Thank you so much for your patience, Mark, and excited to hear about CUDA Quantum.
Yeah, not a problem at all. Thank you, Danny, for helping to troubleshoot. I'm glad I don't have to do that because that's always the difficult part. Let me see here. All right, is everyone able to see my screen?
Yes.
Okay, so the PowerPoint's up there.
I see it.
All right, I'm not able to see anyone in the corner for some reason how it's loading on my screen. So please just interrupt me if you have a question or something that is important. I'm really grateful for the chance to share a little bit with you. Before starting at NVIDIA, I was actually at Quantinuum, so I've spent a lot of time in the Boulder area, and you're in the proper location if you're interested in quantum, because the whole geography there is certainly becoming a hub. So I'm excited to see that continue to grow out. And what I'd like to do is just give you a little bit of a brief of what is CUDA Quantum, why have we constructed it the way we did, and then give you a little bit of a getting started. This will directly accompany that notebook that we have on the GitHub that has kind of an intro to CUDA Quantum, so you can easily go through and follow along or load it later and get to some of the things that I don't get to. So with that, I'll get started. And really at NVIDIA, we are focusing on how can we use our GPU capabilities to enable quantum computing. And there's kind of two pillars to that. One is on the quantum algorithms research with CUDA Quantum, which is our library for quantum simulation. And so most of what you're going to run on CUDA Quantum will be CUDA Quantum will be on the back end accelerating the simulations you run. But then CUDA Quantum is our development platform to develop hybrid quantum classical algorithms. And in particular, how do we integrate CPU, GPU, and QPU capabilities so they can all run together and do all of these complicated techniques that will have like error correction, control, and actually running the algorithm in one centralized location. I think another way to kind of see that visually is we're expecting that quantum computing in the future will be distributed just like a lot of computing techniques today when we parallelize. So we might have something that looks like this picture here, where you would distribute computations to these nodes, and they each have a CPU, GPU, QPU that take the part of the problem that's best suited for whatever type of hardware. And we want CUDA Quantum to be really easy to learn, fast, because we need to run all of these routines very quickly, and they need to be high performing, flexible, so we can run on any QPU backend, and then also very scalable, right? So we can take these problems from kind of toy examples up to practical scale. So I'm just going to jump right in and get started with how would we build some simple quantum circuits, and what are some of the commands that you're going to be using most often. So in order to define a quantum circuit, we use this object called a kernel. And the kernel is really going to hold all of the information for your quantum circuit, and it's going to be the object that is sent to whatever backend. So whether that's a physical quantum computer or a GPU simulator of a quantum computer, the kernel is kind of the vessel by which that's distributed. So in order to build a kernel, after you've loaded CUDA Quantum, this CUDA Q, you're going to then set a kernel equal to this method of make kernel. And then we're going to allocate some qubits. So we're going to use this qalloc command. And whatever number you put in here will be how many qubits you put on this register that we've named qubit here. Now, this could be, you could make multiple registers. So maybe you have an algorithm where you have some data qubits and some ancilla qubits, and you want to keep those separate. You can do that when you allocate the qubits right on this step. But then after you've defined how many qubits you have in your kernel, you can come and start applying gate operations however you'd like. So here's an example of these different gate operations like a Hadamard gate. And we're applying them to that single qubit that we've made. Now, I'm going to show some examples later that show how you specify which qubit you want to target, or how do you do maybe a 2-qubit gate, things like that. But this is kind of just the simplest construction we can do. And then finally, you'll end. Oh, I'm sorry, was there a question?
Just a quick point to chime in for the students who have been going through some lectures with me. This is very useful information to know how to tackle warm-up challenge 1. Where the warm-up challenge 1 is about making a random number generator, and you'll use the Hadamard gate, that kernel.h. You'll wanna use that. So just to kind of connect this to some stuff we've already kind of mentioned, Mark is really showing us how to tackle warm-up challenge 1 in the syntax of CUDA Quantum.
Awesome, thanks, Joan. Thanks for connecting that to where the students are at. That's super helpful from my perspective. Another note.
Question.
Yeah,
Sorry.
go ahead.
Because Joan, we have the other PowerPoints that you have made. Are we going to be able to get this PowerPoint as well or no?
Yes. I will
Cool.
gladly share this.
1,000%.
Thank you.
1,000%.
And like I said, almost everything I'm going through is in a notebook, so you can just run the code yourself. That's probably easier than looking at my PowerPoint, but either way, I'll provide it. Yeah, so also we have on our documentation all of the gates that we have available, so that's also linked in one of the materials that I sent. And then once you've built your kernel, so you've essentially specified your algorithm, then we're going to say, how do we want to measure? And you can select multiple qubits to measure. You can measure a subset of the qubits. You can decide what basis you measure in. So this is just the standard measuring in the Z basis of the single qubit that we've set up here. So that's kind of building your first quantum circuit. Now I want to look at some of these algorithmic primitives that help us actually do something with that circuit. So there's really three I want to focus on. One is going to be sample, which is how we would, if we've built some quantum state, how would we sample from it and pull out information that way? Another will be spin-op, which is how we build spin operators, like our Hamiltonian, which we'll be using in the VQE examples. And then observe, which is how we determine expectation values. So these are going to be kind of three fundamental commands that you're going to be using probably for the entire hackathon. So let's take a look at a little bit more of a complex example where we're going to build a Bell state. So if you're not familiar with what that is, it's just applying a Hadamard gate on qubit 1 and then a C0 gate between qubit 1 and qubit 2. This just exemplifies a couple things on this example here.
And
how
for the
to
students-
specify. Oh,
Sorry,
yeah.
just what? Sorry, Mark. We
No
saw. I didn't call it that, but we saw a Bell state at the end of last lecture. That was where we, instead of feeding a classical bit into our C0 gate, we fed it a plus state. And we were wondering, what happens if it says simultaneously yes and no, apply the NOT gate on the bottom qubit. That circuit is a very famous circuit called a Bell basis circuit. It makes one of the canonical entangled states that are very kind of core to quantum computing and very useful. So this is how we would make that same circuit I showed you at the end of last lecture in CUDA Quantum.
Yes. And then, as I talked about on the previous slide, if we build this circuit and now we want to sample it to demonstrate that we've actually constructed what we intended to, you simply call this CUDA.sample method. You're going to input as one of the arguments the kernel that you've built, so the kernel we defined previously, and then how many shots you want to take. So how many times we build the state and then sample and measure to kind of get our sample statistics from the quantum state. And if we print the sample result afterwards, you can see that we get 1,000, just about 1,000 of each measurement of a 0, or a 1, 1. So if you're thinking back to that last lecture, these should be the kinds of measurements that you get from a Bell state. And I'm sure you can discuss this further as you learn more about the theory. But the point of this is if you built a quantum state and then you measure it with the sample technique, you can spit out a dictionary of all the different bit strings and the counts that you get for them. So that's going to be a really important mechanism.
Chime in again really quick just to connect it again. We haven't talked about measurements yet. That was going to be the next lecture, was to talk about like how you extract information. We did talk about how an individual qubit, measuring it is like looking at Schrodinger's cat. It's randomly a 1 or a 0. And with a Bell state, what the use of the Bell state is it creates between two Schrodinger cats a set of options that are not totally random. Meaning, with regular, just uncorrelated randomness, one cat could be alive, the other one could be dead. They could be both alive, both dead, or any permutation of those, 4 options. What the Bell basis is doing is creating a random superposition over half of those total 4 random outcomes. So you're only expecting to see 0, 0 or 1, 1. You can't see it when they're disagreeing, at least in this setup.
Yeah, so that will be a really good, I think, as part of the warm up to go through and play with that circuit and experience that for yourself as you build the state and measure it, because these are included in the notebook as well. If you haven't had a lot of experience with measurement, this might not be as useful yet, but I think it'll be really helpful to have these kind of commands as you work on the hackathon challenges. On this slide, there are just a few different methods to pull different information out of all your samples. So if you built some quantum state and you measured all the bit strings that you can get, and hopefully we'll talk about that more and more in the next few weeks, you can ask for things like, what's the most probable bit string measurement that we get from all the qubits? And that's a really important piece of information from a sample like this. Or you could ask for, what is the count that I got for the 1-1 state? So here I'm saying, hey, what is, if I sampled 2,000 shots, what is the count that I got for 1-1? And that's 993. And you can also ask for the associated probability, things like that. So those are going to be really useful as you build quantum circuits and extract information out. And again, there's all in the documentation, these kinds of methods that are listed. I'm going to move a little bit ahead, and my guess is Joan, is it correct? Probably have not talked about operators yet.
We've talked about rotations. So the students have
Okay.
seen X, Y, and Z rotation gates, and I've introduced how you build a Hadamard gate from rotations. And in the next lecture, I was going to introduce them to the Paulis, but Jackie and Abby, if you see a Z or an X or a Y, these are just, special cases of the rotation gates that are useful in many applications. So people tend to specify them as their own thing that doesn't depend on an angle because it's got some fixed value. But again, Paulis and measurements were going to be with the very next lecture.
Awesome. So as you go further through the content, one of the really important pieces of quantum algorithms, and particularly a lot of near-term algorithms, is encoding your problem in something called the Hamiltonian operator. So the idea will be that you'll maybe have some molecule. So when you're looking at the VQE challenges, I think some of them will be focused on chemistry. This Hamiltonian will be specified a certain way. Or other problems have very simple Hamiltonians where you're going to build them up with these Pauli strings, or into these Pauli strings with these spin operators. And that's done in CUDA Quantum with the spin-op command. So I'm going to be kind of high level with this, but you can basically say, I want to do a Z operation on qubit 0, and you can specify that with the spin.z command right here. But you can also do any kind of combination or product of these different kind of operators. And so when you're working on actual problems, you'll be doing this quite often to encode the proper Hamiltonian. And I'm just going to skip through a little bit quicker here. Once you've built a Hamiltonian, one of the important things we want to get from that is an expectation value. So in a chemistry setting, the Hamiltonian would produce the energy of the ground state energy of a quantum system or of a molecule. So you might have encoded, say, the water molecule, and then you have its Hamiltonian, and you want to compute that expectation value from that quantum state and that operator. That's done in CUDA Quantum with this CUDA_Q.observe. And all you do is specify a kernel like we've been doing in the previous slides. So that's your quantum circuit. And then you specify your Hamiltonian. And then you're going to feed those into this CUDA_Q.observe. And so the kernel is an argument, the Hamiltonian is an argument, and then you take a certain number of shots. And with that, you'll produce an expectation value. So that's going to be really important for the VQE challenge, because that's kind of the core, is to build different states, measure expectation values, and then adjust them.
And just to chime in one more time, so Jackie and Abby, a lot of these terms will be unfamiliar, but they're not terribly foreign. All a Hamiltonian is an energy function. And an expectation value, another word for that, is an average. So all we're doing with the VQE challenge is we're figuring out a quantum circuit that minimizes the average energy of a molecule, which is very helpful in chemistry. If you know the minimal energy of a molecule and you know the next energy up from that, you can predict a lot of its reactive properties. And so the use of this is that we get to be able to simulate on our computer some of the reactive properties of a molecule if we're able to minimize the expectation value of the Hamiltonian. So physicists love to use our own terminology for things, but these concepts are not totally alien. And again, all this stuff is stuff we'll be talking about next time. And warm-up challenge number 3 is intended to give you a bit of an introduction to VQE in general as well. Go ahead, Mark.
So, Joan, given time, are there any time constraints on your side, or would you like me to keep going a little bit longer?
Yeah, how much more
I'm
time do
happy
you
to.
have? I see you have quite a bit more slides. I apologize if my chiming in has slowed you down a little.
No problem. And it's helpful to adjust to what the participants are familiar with. So
yeah,
I'm not going to get through all of these, and I never intended to.
For sure. I do have another meeting, but I've told them, folks in my next meeting, I'm going to be a little bit late. I do want to get the recording of these slides together so that we can share them with folks and people can watch them afterwards. So let's try to finish this. Maybe I can run 10 minutes over at most, if that works for other people.
Yeah, let me skip to what I think will be. Yeah, that sounds great. And I'll skip to what I think are most important, because not everything in here is going to be critical.
Well, the slides that you skip, you can always just go back to your access.
Oh, I'm sorry.
Okay.
Your room is quite loud.
You can always go back.
Sorry, Abby, I don't think I could hear that. There's a lot of feedback.
I think she was saying that we could always just go back to the slideshows afterwards.
Absolutely. So I'm flexible with whatever would be most helpful. I can jump to some of the parts that I think would best serve you for these challenges. Or you could just reference the slides later.
Yeah, maybe talk fast through the slides that you think will be less relevant to the challenges, and maybe spend more time on the material that's directly relevant to those.
Perfect. So moving on to kind of the next level up, and this will be really important for VQE, because the point of VQE is to build a quantum state that's parameterized. So you're going to have these different parameters in there that can be tuned. And as you tune the parameters, but keep the Hamiltonian the same, that will lower the energy or raise the energy of the expectation value you're computing. So the goal of VQE is to minimize that energy. So if I tweak these, in this case, we're going to call them thetas. If I tweak these thetas, the energy gets lower and lower and lower, and then that's the solution I'm looking for. And it's essentially an optimization problem. So building a parameterized circuit is what you're going to need for that. And the only thing that's different here is that when we make the kernel, we provide this extra object here called theta, and that's going to be an empty list. Then when you come to any gate that's going to have a parameter in it, like this RY rotation gate, we're going to say, okay, this parameter's theta 0, this parameter is theta 1. And then when we get our expectation value and do a CUDA Quantum dot observe, we give it the kernel, Hamiltonian, and these parameters that we'd like to put into here. So this will feed this parameter into theta 0 and the second parameter into theta 1, and it will compute that expectation value. So in a VQE computation, you're just going to tweak those parameters and keep doing this over and over as the expectation value gets less and less. So that'll be something.
Sorry, Jackie and Abby, we talked about this a little bit when we introduced the rotation gates. The idea is you don't know which point on the block sphere, which quantum state for the qubit helps you minimize the overall energy of the molecule. And so this is our way of searching over all the different possible angles to find the correct way to prepare that minimum energy. Also, Mark, could I ask you a question about CUDA's
Yes.
functionality? So I saw in the guide, and you've got it here too, that the way that you're having folks input a Hamiltonian is by specifying the precise linear combination of all of the Paulis. In other packages that I've used for VQE, there's been some functionality to just say, I want the Hamiltonian of the a hydrogen 2 molecule or lithium hydroxide to specify the molecule. Because like a priori, if I were trying to help a student and we needed the Hamiltonian for lithium hydroxide, I wouldn't know what that was off the top of my head.
Absolutely. So I would not either. And I come from a chemistry background, so no shame there. There is, I think we plug into Open Fermion, I think. I'm just trying to remember which. There is a chemistry tutorial that I've linked to in my Getting Started guide, or the challenge guide. That does show how would you call a chemistry package, plug in a molecule, plug in a basis set, and it would spit out the Hamiltonian. So yes, that is something we have built in. I would not expect anyone to do that by hand. This is just kind of a showing from scratch. Yeah, so one other thing, and I'm not going to go in depth on these details, but one thing I want to highlight, just talking about how CUDA Quantum runs its computations. There's a command called set target, and this allows you to define what is actually going to run your quantum kernel. So by default, the target is NVIDIA, which means it runs on a single GPU. And if a GPU is not available, it'll run on a CPU. But there's a handful of other important targets. There's going to be this mGPU, which can allow to pool multiple GPUs to run a really large simulation. And I don't think that'll be something that'll be relevant for this challenge and given your GPU infrastructure you're using for the challenge. But I just want you to be aware that there's some different tools. One that might be really useful, there's this simulator called Density Matrix CPU. If you wanted to add any noise to your simulations to more mimic a real device, you would just use that simulator. And I have some slides about how would you introduce some noise, but that might be beyond the scope of what you're looking at, but could be an interesting extra add-on. And then we can also target a variety of different QPUs. So if you happen to have access to a IonQ or something like that, you could actually run it on the real hardware. In all of this, one thing I want to say that's part of how this is built is to parallelize a lot of your computations. Don't look in depth in this code. I just want to give an example. We talked about sampling earlier, and if you're sampling from a quantum state many times, you could also do that on multiple QPUs. So we've built this functionality where you could run these simulations on 4 GPUs that are simulating quantum computers and get samples back 4 times as fast. So there's a lot of examples in CUDA Quantum of doing things like this. And some of the challenges require you to think about how could you parallelize these sorts of algorithms. So just wanted to highlight that, and the slides have some more examples. Yeah, one more I want to mention. We do have a VQE method that is pretty similar to what we've been talking about before, where you provide a kernel, you provide a Hamiltonian, and then the only difference is you're going to also feed it an optimizer, and this will do all the work for you to tweak the parameters, measure the expectation value, and continually do that until you get a minimized energy for the system. So that can be easily done with this VQE method, and it's not so different from all the things we've talked about so far. The only difference is you're now feeding it an optimizer to do that optimization procedure.
So Abby and Jackie, that looks like that method, that VQE method, will be a really nice way for you to solve my warm-up challenge 3 that would prep you to solve the NVIDIA adapt VQE challenge as well. Looks like they've taken a lot of the guesswork out. That's very nice.
And there's also ways, and we have some examples where you can not use the VQE method and you could just run a normal optimization, kind of do it manually. So there's multiple functionalities for getting the same result, but the wrapped up VQE method is pretty nice. Let me just end here because I think everything else is more advanced applications that you may or may not find useful, but they're there if you want to reference. I want to point to two things down here. On the CUDA Quantum GitHub, we have a tutorial section, which are some notebooks of some particular examples. And we have an examples section, which are more just Python scripts. But those might be really helpful because if you click on this link, there's a chemistry example. There's some other ones that might be relevant. There's some showing how do you add noise into the system. All of that, I think you will find very helpful to seeing some more sophisticated CUDA Quantum code and how it could apply to your work. So just to kind of summarize, the sample method, spin operator, observe, and VQE are probably going to be the most common things you're going to use. And CUDA Quantum also has a lot of examples of how you can parallelize. So you can go back through the slides and kind of look at those, whether you implement them or not. I think that's a really interesting aspect of the code. So with that, I think I'll stop there. And I think you would be best served to go play with the notebook and do it yourself and kind of experiment. But I'm happy to take any questions now if there are any lingering.
All right. Thank you so much, Mark. And we'll just go ahead and thank Danny as well. Thank you both. This is really nice.
Thank you.
Okay, for the
You
sake,
both too.
do we have any quick questions? For the sake of time, I do need to use this room for the next meeting, but I'm going to stop the recording.